we're going to look at basically how the energy of a compound changes as ionic bonds are formed. Okay, we're going to look at like a little bit more in depth into the process of an ionic bond, how a cation and an anion truly actually form that bond, right? We've said before that ionic bonds happen because an electron's traded. Well, that's true, but there's several steps that go into that. So the goal today is really to look at energy in a bonding and how the formation of an ionic bond really takes place. It's pretty interesting. It's called the Born-Haber Cycle. Okay, it's a kind of just process in which cations and anions go through, or really neutral compounds go through to ionize and then form. So, all right. It says, what are the factors that influence the stability and structures of solid binary ionic compounds? So I listed some solid ionic binary compounds there. Any sort of, let's break down what is binary ionic compound. What's that mean?
2 elements.
That's right. An ionic compound that contains 2 elements, right? So any sort of ionic compound that contains 2 elements. Okay. This concept of lattice energy estimates the bond strength of ionic compounds, okay? It's the heat of formation of opposite charge in the gas phase to combine into an ionic solid, right? Heat of formation for ions of opposite charge in the gas phase. So heat of formation we talked about in our last chapter, okay? I think in our calorimetry chapter, what was the change in enthalpy when a chemical reaction happened, all that kind of stuff. And so now we're looking at heat of formation for the ions themselves, not the full, we're looking at the heat of formation for the compounds themselves, right? We looked at heat of formation for whole reactions, and we took those values from the book. Remember how we looked in that table in the book for heat of formation? So now we're really finding out how is that number calculated, right? How is the heat of formation number calculated? Okay, so lattice energy is the energy it takes when separated gaseous ions are packed together to form an ionic solid. So something you probably didn't really understand or maybe didn't know ahead of time is that these molecules tend to form out of other states of matter, right? Not always necessarily solid. This says gaseous ions are packed together to form an ionic solid, okay? So this equation is for lattice energy. It's not going to be our main focus of the chapter, I'll tell you that, but it is something that we have to kind of look at here in terms of the energy formation there. Okay, because we'll see how these ions or metals and nonmetals become gaseous to then form. Okay. K is proportionality constant. That'll be given to us in the problem. Q1 and Q2 are the charges. So if one is plus one or plus 2 or plus 3 or whatever it might be, and then R is the atomic radius, right? The distance between the centers of the cation and the anion. Okay. I just want to introduce lattice energy, but I said we're not going to focus a lot on that for the chapter, right? Now we're going to really walk through the steps of what it means to form an ionic solid. Okay, this is called the Born-Haber cycle. Okay, so I want you to maybe write that up at the top of that slide. Okay. Bornhaber, Born-Haber cycle. All right, and it goes through several steps, 5 steps to be exact. Okay, did I write the steps out for you on your slides or not really?
They're blank.
They're blanks. Okay, so I'm going to give you a second to get them written down, and then I will walk through what each step kind of means. Okay, so I'm going to give you some time here. Let's talk through what each of these steps mean, okay? The first one is sublimation of a solid metal. So what does sublimation mean? Sublimation is going from a solid to a gas in one step. Okay, so we go all the way from solid all the way to a gas in one step. It says that process is endothermic, which means what? Heat is going which direction? Into, right? That makes sense, right? Because we're going from a solid to a gas. So it's endothermic. So these listing of the states of matter for this is really important because we've got to know, are we dealing with magnesium solid or has it already been sublimated, right? Has it already been turned to gas? So in the past, we weren't super concerned with states of matter, but this one we really are. Okay, so these states of matter are really important. So step 1 is sublimation of the solid metal. Okay, that's if I'm going to give you the steps on something, that's what I'll put. And you have to know how to then apply that thing. Okay, sublimation of the solid metal. You'll be given a number value for that. How much energy does it take for that to happen? Okay, and so we'll walk through what that looks like here in a little bit. But step 1 is sublimation of the metal. Step 2 is ionization of the metal atoms. So what does ionization mean? Yeah, to ionize something is to give it a charge, right? To make it have a charge. So tell me what magnesium's normal charge is. What does magnesium like to have? Plus 2, right? It's in group 2, so it's a positive 2. So what happens in this example with magnesium is that magnesium gas, heat flows in, and magnesium is ionized, which leaves us with magnesium plus 1 and an extra electron, right? An electron is plucked off during this step, okay? This says we could have multiple ion levels of ionization. That would be the case for magnesium because we need to get magnesium to a plus 2 charge, right? So this step would happen twice. Does that kind of make sense? The first one would be, for example, this, right? M to M plus an electron. Part 2 of that step would say Mg plus as a gas would yield Mg plus 2 plus another electron, right? We pluck another electron off, which results in us having Mg plus 2. Okay, so that electron we plucked off, it doesn't go to nowhere. We're going to use them in later steps. But we've got to show that we removed an electron from magnesium, which takes us from plus 1 to plus 2. Yeah?
Why wouldn't you add an electron, why wouldn't that be on the left side of the arrow? Because then it'll result in plus 2.
Right, but we don't want to add an electron because that would take us back to neutral. Right, plus 2 means we're short 2 electrons. Oh. So we're plucking another electron off. If we needed to get something to a negative charge, you're right, then we would add in an electron. And we're going to do that later, actually. Okay, so this one is this would leave us with plus 2. This corresponds to the ionization energy of the metal. Okay, there's both a first ionization energy, which is how much energy would be required to do this step, and a second ionization energy, which is how much would be required to do that step. Okay, do you remember when we talked about ionization energy and periodic trends? Right, it's literally the amount of energy it takes to remove an electron. Okay, so we'll look at those when we start putting numbers with it. Okay, now I'm going to give you steps 3, 4, and 5. Okay, so go ahead and write these down, and then I will walk you through them as well. All right, so in steps 1 and 2, we really prepared the metal, right? We prepared the metal. We took it to a gas form. We ionized it, and so now it's ready to go. Now we're going to shift our focus to what needs to happen to the nonmetal, okay? First thing that we have to do is dissociate the nonmetal. So dissociate means we take it from being bonded like a diatomic, and we separate it. So now it's just by itself, okay? You'll see this 1/2 up here to represent, you've got 1/2 of the mole of that, and when we separate it, leaves us with just X, okay, or just the molecule itself. Right? Because 1/2 of X2 is just X, okay? So we dissociate that. We get it to just be the element by itself and not part of a diatomic, okay? In this step, the numerical values we're given are usually given per mole, so we need to pay attention to whatever our starting mole ratio is. Whatever our starting coefficient is, we have to pay attention to that, okay? All right, number 4 says formation of the non-metal ions to the gas phase. So we need to take our non-metals and make them ions. So you know the electrons we plucked off in step 2? Here's where they come back and they get added to our non-metal, which makes it now a negative ion. Okay, again, this is called electron affinity, how much energy is required to add an electron to that atom. So we've used both ionization energy and electron affinity in these problems. But again, this could take multiple steps. If we have to get it to a negative 2 charge, like we did in the last one, we've got to do it 2 times. Okay, so we'll look at that as examples come up. But these electrons aren't coming from nowhere. We removed them from our metal, and now we're adding them to our non-metal in this step. Okay, so then step 5 is just the formation. Once we've got our cation ready and our anion ready, both in the gaseous phase, then we can call it now our new solid. Okay, when they form, they'll form a solid ionic compound. This last step, the formation of the actual compound, is considered the lattice energy, right? How much energy that step takes is called the lattice energy. Okay, so I know this seems like way crazy right now, but I promise when we start doing the problem, it'll make a little bit more sense. It's very systematic. You're going to walk yourself through steps 1 through 5 and figure out how much energy really did it take to form this ionic compound. Yeah. If it happens that our nonmetal starts as a liquid, we would add in like a 3A step here to put ours from a liquid to a gas, and that would be like whatever that energy would be given to you to make that happen. Go ahead, Kristen. Of the Born-Haber cycle and how it works in 2 different compounds. So on the left, MgO is being formed. Okay, so here is MgO and its formation and its overall energies. And then NAF is on the right. So I want you to think about, why are these energy levels so different if we're forming binary ionic compounds? What would make the formation of these 2 compounds so different?
Magnesium and oxygen have a higher charge.
That's right. Magnesium and oxygen are both 2s, right? Magnesium's +2, oxygen's -2. And sodium is +1, fluoride's -1. So magnesium and oxygen had to do a lot more work to get up to that +2 or -2 charge, right? You see the difference in ionization energy right here? It's really high, right? To ionize that molecule, it took a lot more work for that to happen, right? Because it had to do it twice. Magnesium had to get 1 electron pulled off and then another. And then oxygen had to get 1 electron added and then another. So it takes more energy to form those types of molecules than molecules with a lower charge. So, yeah, good. Let's go ahead and try one here, okay? Use the following data to predict the heat of formation for potassium chloride. So our original reaction is given, okay? The reaction is given itself, but we've got to walk through the steps, okay? Because we start with potassium solid and 1/2 of a Cl2. And our goal is to end up at KCl. Okay, so I'm going to write out the steps like we usually do. And I want you to do that with me. So what do we say step 1 is? Sublimation of the metal, which means, okay, I like to go ahead and just write out, this is step 1. Okay, let me make my pen a little smaller actually here. And I'll go green, because why not? Okay, we start with potassium solid. But we need to get it to potassium gas, right? That's sublimation of the solid. We did not have any mole ratio up here that we've got to consider. So we're going to go to our data table and say, where's my enthalpy of sublimation or my energy of sublimation? It's way down here, right? So I'm going to come over to the side and just going to write plus 90. Okay, kilojoules per mole.
Will it give us the chart of all the energy?
Yeah, it gives us all that information. Right, so we're not going to even search them out, right? We've just got to put them in the right order. We've got to apply them correctly. After I use one, I usually kind of like to, cross it off or exit out so I know that, I'm not using that again, right? Just to give myself a little more clarity on that, but you don't have to necessarily do that. Okay, step 2 is what?
Wait, that's all you have to do for step 1?
Yeah, that's it. I wrote it out because right now I'm left with potassium gas, right? I've done that step. So step 2, I'm going to take my potassium neutral gas and I'm going to do what to it? I'm going to ionize it. And so that once I ionize it, that leaves me with K plus in the gaseous form. But I've got to include that electron that I plucked off. Right? It's not on the reactant side because the electron that I removed from it is now a product of that reaction. Right? I ionized potassium in gas form to remove that electron. So that is called what? Ionization energy. And I only had to do it one time. So you might even see it labeled as first ionization energy, right? You might see that in some tables. If we had to get it to a negative charge, there would be another number there that says second ionization energy, but we didn't need that for this one.
So
Yeah.
Do you have to keep moving the 90 down?
We're going to add them all up at the end.
Oh, okay.
Okay, so we're going to use, just going to make a list here of our numbers. So plus 419 kilojoules per mole. Okay, can you guys see that okay out there? Is that okay?
How do you know
I look at my final one here and I know that it's going to be a 1 and a 1.
Gotcha.
That's it. Does that answer your question?
Yeah.
Okay. That's okay. No problem. Okay.
Yeah,
That answers your question? Okay, good. We know that based on our final product, potassium is +1, chloride's -1. So that's how I know. You would also know, like, if you've got a second ionization energy listed in your table with your numbers, like, that's a pretty good clue that you're going to have to do it twice also. Okay? So I used that one. Now my step 3, right now my metal is prepared. Right? My metal is ready to go. Okay, step 3 is what? Okay, step 3 is, what is it called? Dissociation of the non-metal. So I start with 1/2 Cl2. And when I break that apart, I just end up with Cl. And it's in a gas, right? Because it started in a gas. So, right, I don't have Cl2 anymore. I just have Cl. But what we have to pay attention to here is that the the bond energy, the breaking of that bond is 239, but I started with only 1/2 of that. So I've got to take that divided by 2. So I'm going to say 239 divide by 2 kilojoules per mole. Okay, yeah, you can do it there, you can do it later, it doesn't matter.
119.5.
Okay, so if you're going to write out 119.5, and then I'm going to go ahead and just cross that out so I know I did it.
Do you have to write it out, or can you just divide it first?
You could just do it first. I just write it out so I know that I did it. Or you could come over here, right, and you could say divide by 2. That way you remember that you did. Like we made little notes when we did Hess's law. So, all right, so that's done.
So if
All of our data here is given per mole. So if our mole ratio is anything besides 1, we've got to adjust that value. Yep, good question. Okay, so now I'm left with neutral chlorine. So my next step is to make chlorine not neutral anymore, right? What's that step called?
Formation of non-metal ions in the gas.
That's right. We're going to use our electron affinity now to add the electron we plucked off of potassium, add it back to chlorine. So we're going to take chlorine neutral. We're going to add in that electron, right, that we pulled off over here. It's just waiting right now. We're going to add it in right here, and that will leave us with Cl- as a gas. Okay, and that is called the electron affinity. Negative 349 kilojoules per mole.
For this one, since we already did the dividing by 2 thing, do we need to divide this by 2?
No, that's right. Because you're looking always for what you start with in your problem here.
Okay.
Right? Since I've already got it to a 1, I don't have to do anything there. But since here I started with a 1/2, I had to use that math with my energy. All right, so my last step now is putting them together, right? I've got a cation that is prepared and an anion that is prepared. And so now we're going to put them together. Bless you. Step 5 is formation of my solid molecule. Is that what it's called?
Yeah, formation of solid.
Okay. So I'm going to take, bless you, potassium plus in a gaseous form plus chlorine minus in a gaseous form. And it's going to give me KCl, which will be in a solid form. That is the lattice energy, right? That's the actual putting together of those molecules, of those ions. And that lattice energy was given to us as negative 690 kilojoules per mole. And so that means the heat of formation is going to just be an addition of all of that stuff right there. So we're going to add up our whole list there. Find out the lattice energy using a Born-Haber cycle. So this one, they gave us like the answer, right? We've got a missing piece. So it's no big deal. It's like all your numbers plus X equals the answer they gave you, and you're looking for one of those pieces, right? No problem. So let's try that.
So the enthalpy of formation.
The enthalpy of formation is like what we had in our last one under our equals. You know what I'm saying?
Couldn't we find this on the boundary on the work though?
I don't know how. Mole ratios, right?
That's the
Yeah. All right, so let's start it here.
So I got it.
Okay. I'm gonna have to try to write kind of small here. All right, so step 1 is what?
Solid to
Yeah.
All right, we're gonna take 10 solid to 10 gas. That's called sublimation. And that's plus 303, right?
Yep.
And we only started with 1 mole. So we don't have to adjust that number at all. Okay, is this on the board big enough for everybody to see? Okay. Okay. Step 2 is ionization. What do we need? What are we going to have to get our tin molecule? What's the charge we need on it?
Is it just its regular charge?
Yeah, I mean, look at it here. If it's bonded with chlorine, what do we need that charge to be? SnCl2. What do we know it's going to have to be? It's going to have to eventually get to +2, right? Because chlorine is always -1. Chloride is always -1. So it's going to have to get to 2. So we're going to have to do this in 2 steps. Okay? So we're going to take tin as a gas. We're going to remove 1 electron. That leaves us with 10 plus 1 plus that electron. That would be the first ionization energy. You see how we've got 2 listed? Okay, first ionization energy. Okay, sorry, we used heat energy of sublimation. I'm going to cross that one off. Okay, so this would be plus 709. Then we're going to do it again. I don't put a new step in because this is still part of step 2. We're going to take Sn plus 1, and we're going to remove another electron. That leaves us with Sn plus 2 and a second electron. Okay, you see how I did that? I took my product from here and I brought it down as my reactant, and then I pulled off another electron, which results in that +2 charge. Does that kind of make sense for everybody? Mm-hmm. Right? And here's our 2 electrons we're going to have to end up giving for each chlorine molecule later, each chlorine atom later. Right? Because we've got 2 chlorine atoms we're going to have to be taken care of later. Does that kind of make sense? Law of conservation of mass says they're not going anywhere, right? We've got to rearrange things. So, all right, very good. Second ionization energy is...
This is
1,400.
I was just getting that number up there. Okay. Now, yeah, tell me step 3 now.
Wait, it's 12, not 19.
Dissociation.
Oh, sorry, thank you. Dissociation. All right, so I'm starting with Cl2 as a gas. And I'm taking it to what? If I'm breaking that bond, right? This is what's happening in this step. We're breaking the bond between Cl2. And when I do that, what am I left with?
Cl.
Okay, but how many?
2.
I'm left with 2 Cl.
Wait, but don't you want Cl2 in the end?
I want 2 individual chlorines to bond to this tin. Right? Because this molecule looks like this. Tin with a chlorine with another chlorine.
So does
Right?
that mean we're going to have to do 2 bond energies?
Not right now because the 2 didn't start on our reactant side.
Okay.
In our next step, when we ionize those, then we'll have to use that. But for right now, we're breaking a Cl2 apart, and we're left with 2 individual chlorines. Okay? In our last example, we started with a half of a Cl2 molecule, which was just 1 Cl. Right? But now we're started with a full Cl2 molecule, and we break that bond, and so that leaves us with 2 individual Cl molecules. That kind of makes sense? Okay,
I'm
yeah.
confused because like the N, like on the product side, it's tin, chlorine 2.
Mm-hmm.
But so why wouldn't we want to keep it?
Well, because if we leave it as Cl2, that's a molecule that's bonded to itself, and its octets are already full. It doesn't want to bond.
Okay.
We need them to be separated, and we need them both to ionize to be able to get back connected to tin. Okay, does that make sense? Yeah. Okay, so that step was bond energy 242. Now I'm going to take step 4, which is where we add our electrons. So we start with 2 Cl molecules, which are gas. And we add in the 2 electrons. Okay, because we've got an electron from both steps here. Don't we have 2 electrons we've got to put in here? Now they don't will both electrons go on each the same chlorine, or will they both go? Will they separate and go one and one?
101.
Okay, so we've got 2 chlorine atoms. Each one will get an electron. Okay, each will get 1 electron, which will leave us with 2 Cl negative molecules. 2 Cl negative ions. Okay, how do we feel about that part of it?
And then do we multiply?
That's right. We take our electron affinity times 2. Negative 349. We're going to take that times 2 because we had to do it twice. 2 chlorine atoms both needed an electron. Okay? Or each needed an electron. Sorry, I'm going to move my numbers over here a little bit.
I'm sorry. I know I had
I'm going to move these to the side a little bit so we got some room to see what the difference is.
Yeah.
Okay, so that gives me what? Did you guys multiply that already or not?
Negative 698.
Negative
I have
698
grade socks.
kilojoules
I'm not
per.
getting pinched. Alice almost pinched me.
Okay. Now the last step, we've got prepared ions. We have 2 Cl minus and we have an Sn plus 2. So step 5 is our lattice energy step. And that tells us we've got Sn plus 2 plus 2 Cl minus yields SnCl2 solid. Okay, but this is where our question mark is. We don't know the lattice energy. That's our goal, is to solve for that. But we know all of this equals the enthalpy of formation, which is negative 325. So I'm going to add all of these up, right? Plus question mark or plus x or whatever you want to call it equals negative 325. And I'm going to solve for what that lattice energy is. Okay, does the algebra part of that make sense?
Yeah.
Okay, we're just solving for that x, basically.
Ooh.
It comes out pretty big negative here, right?
I got a positive. I got a big positive.
I'm talking about the question mark itself comes out positive. So let me write it up here in a different color. When I add all of those numbers up, that gives me 1968 plus my question mark equals negative 325. So now I'm going to subtract this over, 1968. And I get my lattice energy equal to,
Negative 1,640.
no, I don't think so. Because that 325 is negative. So I think it should be negative 2,293. Is that what we got?
Yeah.
Yeah.
Okay. So my lattice energy is negative. Remember, lattice energy is exothermic, so it really should come out negative.